As I told you.
No, I don't see the. Okay.
This morning.
No, it's not. And back. Is that? And back. This one? Yes.
So it's not stable.
No, I know. It's empty.
Dan, it's a pleasure to meet you. Finally, I'm Frédéric Tillac from Direct. Comfortable.
I was visiting once. I was in Toulouse.
We are at 2 kilometers, no more. It's not exactly. So you introduce Dan and then you will join.
Good afternoon. I think we are ready to start the afternoon sessions and the afternoon activities. So please take a seat. As you know, we have a tight program and we don't want to skip any talks. So we would like to start as soon as possible. So please go fast and take your seats. So then, let me start with the introduction of Mr. Dan Friedlander. So, Dan Friedlander is somehow a well-recognized person in the space sector. I don't know if you give the numbers, Dan, but he is already retired and he has already more than 40 years experience in part testing, part selection, mainly for space. So as you can imagine, he already suffered all the kind of different problems that you need to, let's say, suffer when you are doing parts procurement for space. But in addition, and that is why Dan was invited here, that he was one of the first in using extensively cuts for space during years. And so I encourage you to take some impression about which was his work and which are the myths that they consider when we're speaking about cuts. And probably today we will not have time for having questions, but Dan Friedlander will be part of the panel 2 round table. So if you can wait some of your questions and use this panel 2 for discussion. So then, Dan, is your time.
Okay, good after lunch. It is not the ideal timing of such a speech. But anyway, don't have any choice. Where is the... Okay. Now, those 2 sentences, I put them there because those are the fundamentals of solving the problem, not solving, but trying to transit to codes. Because the transition is it looks like it's a very slow motion. Don't close your eyes. That does not mean that don't sleep, but it means that don't close your eyes. Face the reality. Okay. Open your mind. That means don't be stuck with old things. Now, let us go to the basics, because I didn't here some basic things. So this term quartz, it's sometimes very misleading. Quartz, it's we are talking at a component level. Of course, there is also product level quartz, the so-called non-developmental items, but the military is saying. Commercial of the shelf refers to a huge population, okay? You cannot say quartz in space like my title is, because it's not all the quartz are suitable for being a candidate for space. So what it means, it is not a good idea to do generalizations, because they are hasty generalizations. Mark Twain told about this, that all generalizations are false, including this one, including his own. Now here we see what is the components quartz meaning, and we see that only a small part, like 25%, are maybe candidates for space. The other, I personally don't touch them. Okay. So one point here, when you say quartz, and also within the 25%, not every quartz it's okay. Now I heard many things about here, about automotive. I cannot go into detail because I had also write an entire article on that, but I don't know, I do not understand what is so enthusiastic about automotive. Automotive, if you are going in depth, I don't see many differences between automotive and industrial part. For me, industrial or automotive is the same. Also, you have to keep in mind that automotive is a very narrow range of components, only those for cars and so on. This is one thing to keep in mind. The second is that if you rely on the cars heritage, the car makers are not buying the parts, the automotive parts, as you buy them. They are automotive parts that are bought according to the specific manufacturer's SCD, and you do not know what extra things that requirement put it inside. And the free market automotive, it's according to the AEQ, AEC, whatever spec. In addition, by the way, this was not in my presentation, but I see that everybody is enthusiastic about it. If you look into this AEC, I think it's 100 or 1000, you will see that the automotive it's addressed especially to the cars, especially to an extended temperature range. And this thing is not important for space. Okay, it's the other way around. In space, the temperature range is very narrow, and you do not need this temperature range, extra temperature range, above the military even, what was military. Okay, that's what I wanted to say about automotive. If I have a component, automotive and industrial, I would go for the industrial, and I don't see many differences. The automotive, by the way, if you are looking in depth and carefully read the spec, it consists of nothing, because qualification is only one time, by the manufacturer itself. No screening, so if you adopt I am ready to adopt the automotive, and then you recognize that the screening is not valued, and I am agree with that. And many other things that people think that this means something grandiose. This is not true. In the industrial, they are doing the same thing, even if sometimes or many times it's the same component. And don't believe that the industrial parts are not qualified, not qualified, and not reliability monitoring and all those things that were once in the military. Every manufacturer, not every, but the manufacturer that I am talking about, what they call in best in class, that can become selected for candidacy, have all these QA means inside, and you can see them in the website. Now, what are the characteristics of codes for me? High volume production, okay? The high volume production, the statistics works for high volume. It does not work for small volume. Because of that, the military at the time, in 1960 or something like that, when they wrote the military spec and so on, they didn't have the high volume because there was small volume of the military, and then the statistic does not work well. So they couldn't exploit this source of statistics, and they instead, in also to compensate the lack of the statistics, they put in heavy testing and screening. The situation today is completely different because now the production lines are high volume. They can use statistical process control. Okay, that is a tool that addresses the production of the die. That is the essence of the reliability. So I think the reliability issue was not stressed enough. Because the high volume, the lot homogeneity it's better, and the value of sampling is higher. That has an important meaning for policies like we have done. Of course, there is no screening. Okay, that's true. Now, what happened was there are global developments that you have to face them. You cannot disregard them. One of them was the decrease of the military and space components market today to 0.1% of the world market in dollars. It was 60% in 1960. In 1960, the military and they have observed many failures in the plastic parts. It was at the beginning. From then, I think 60 years now, many things happened that changed the situation, and the specs are still not considering this. The component availability, the military, the many components manufacturers has massively left the military market and left people without them, without even notifying them sometimes. So that is the situation. there was also, of course, huge technological progress in solving all those infant problems that they had because of the production and so on. Now, that global developments led us to a cultural change from use of military to use of commercial. Now what was the idea? In 1994, the Secretary of Defense of US has decided, or has issued a famous memo that legalized the use of codes in military applications. We are talking now about military only. The space applications are exempted. There are many reasons for that, because first of all, he was not governing the space issue, because he was in the Department of Defense. And secondly, he does not want, also this was very difficult, so he didn't want headaches. So now what was his drive? His drive was that the defense budgets were shrinking, military components, the availability just before these, the manufacturers left the market, many, and of course the performance that were not achieved with the lagging technologies, military technologies. Now, what the memo said, the use of military specification and standard is authorized as a last resort with an appropriate waiver. That means that to use in military application a military part, you have to get a waiver, approval of the waiver. That there was a bureaucratic thing that was supposed to frighten the people. After several years, after this man was gone, there was another guy that succeeded to cancel the waiver. You don't need the waiver, but still is the last resort. And if you look in the papers, also I will come to the space specs also to see that it's the same thing. Now, now the reverse. Now it looks like the order of priority changed. Also, till this moment, to 1994, I didn't touch codes, and because we were dealing with military equipment, and nobody wanted to hear about plastic parts in military equipment. When this happened, our company was put together a team. I was a member of the team. We have done a tour in 18 days tour in US, and we have covered manufacturers and agencies and military and those that are doing the mill handbook to see what is happening. And I was surprised to see that also in military there was a lot of experience with good experience with plastic parts, but nobody talked about it because it was forbidden. Even in the sea, the beacons that float on the sea, they already then, it was 30 years ago, I don't know, they used plastic parts. Now, so it is a big step to recognize officially the global development in an atmosphere of strong resistance to change. In my view, the most important, there are many obstacles to go to codes, okay? But most of them are not technical. one of the most difficult obstacle to pass, to overcome, is the resistance to change. And this is not surprising, because in every aspect of the life, people are not happy to make changes. But if the leadership has the same attitude, so that is reflected in the situation now. Now, what about the cost saving? One was the budget shrinking, and this is one of the main driver. Not only, I mentioned three. This is true for military. It's not true for space. That you have to remember. In space, you won't save money by that. In military, because you buy the parts and you put them in the system and use them as is, so you have a lot of savings. And he was right. Of course, from this point on, we have go only to plastic parts in the military applications. Okay, if we would reach the situation that we can buy coats and use them as is, this would be the ideal thing. Not the ideal, but now this global development dictates us to find a new methodology to deal with the costs for military project and for space also. Now, what was done here, the first priority became courts, and the second priority became military. Exactly the reverse. Now, I can tell you from my experience and from others that in the military there is a good experience in using plastic parts. The other thing is, after I have seen this, after some years, it took also me some years, I started to think, what are they frightening me to tell that space is harsh environment? All the time they are frightening people, harsh environment, harsh environment. Now, putting aside the radiation, because this is really an issue, what is harsh? In military, the conditions of the use are much worse. Okay, from every point of view. The temperature ranges, the moisture is there for 20 years, or how much there are plastic parts exposed in the field for 20 years, and nothing happens. And for the mechanical things like vibration, it says during the launch, the plastic parts are much better than the ceramic. Okay, that is for sure a consensus. So I didn't see. I tell to myself, if it's good for military, it's good also for space. Put aside the radiation. Okay. So why not to use them? Because people cut the things to use any codes, okay? Also today, in the ESA spec and in the NASA spec, you will see that now they already recognize the use of codes and so on, but still is the last resort. That is what is written. They say to use codes only if you are compelled to do it, because you don't find the space level. Now, what happened with the military? They went from mere spec to mere performance. So that means they stopped using the cookbooks of the mere spec that tells the manufacturers do it like that, do it like that, all kind of restrictions that stop the manufacturer to the interest to develop in the military field. So the technologies became more and more lagged. Transition from QPL to QML, that means that they recognized the fact that you don't have to qualify every part and every part, but you have to qualify the similar manufactured lines, production lines. And all this is, it was done after many thinking, okay? Not was just that in the morning he did. Now, of course, the components manufacturers get at last, they get the freedom to eliminate justified non-value-added screening of testing steps. Now you can see manufacturers, serious manufacturers, like Texas Instruments, for instance, that for certain families, he does not want to do the burn-in, and he is not doing it, and you can see it in the catalog, because it's worthless. It's not exactly worthless, but more or less. Okay. Now, what happened with the market? The market that was dominated by military now is dominated by commercial. Only 0.1, here is 0.3, but I think already it's a 0.1 percentage in dollars is the market of military and space components. That means approximately, if I'm not mistaken, $1 million. Okay? But what is $1 million for a manufacturer? Not a manufacturer, but 20 or 30 manufacturers that are in this business. So they have to share between them the profit. So, in my view, the manufacturers, it will come a time that they will take a wise business decision, and nobody can stop them, not even the government. We can see them. Even trusty companies in US were sold. So what do we want more? The government has nothing, no power on the manufacturers. We are in the hands of the manufacturers and in hands of business decisions. Tomorrow, some manufacturer that you are using space level parts, it will get to the conclusion that the 99.7% is doing him enough profit, and he can eliminate this sector. So then, that's just started. Okay, I don't want to talk about this. I have many things to tell you about this, but I don't dare to tell you. Not in this forum. But you have, in order to emphasize what is going on at what steps, 2003, you see, the last one, here you see the 2013. Now they say they are working on a new release. So what did they do in all these years? Okay. So let us try to. Okay, miss. I have here 10 misses, but 5 minutes, so I don't know. So I try to shorten it. incorrect interpretation of the term space qualified, okay? What, when you use the space qualified and it was used here, this is something that does not mean too much. Because, for instance, if you are looking at the manufacturer, like analog devices, for instance, or something like that, he says, here is the list of the space qualified parts. Now it is your turn to understand what it means. When they say space qualified in the military, also in the military and also in space, they mean the quality level. Because once the quality level was S, okay, so they say S, it means space, that's okay. Now what about V, what about K, that is now. So quality level is not addressing always, it has to address the radiation, but most of the time they don't, unless they have a designation for RHA. Okay, and what does it mean space qualified? Which space? What mission? What you cannot qualify something for all the space. It's a joke. The main drive to use quotes is those are things that people are telling. You know, there is a party I have invented. A party. It's called RCP, Resistance to Change. Okay, Resistance to Change Party. The main drive to use quotes in space is cost saving. That I already told you. That is not true. You have to compare apple to apple, not price to price. You have NRE, you have RE, you have to add them. Now also comparing apple to apple, space heritage. What does it mean? It was flown in space, so what? Many things were supposed, but what is the mission? What is the orbit? Is it similar to your satellite? Or quality and reliability, okay? Those are two different terms. Some people and many people interchange between them. Okay? I will not go into the definition because I don't have time. Quotes reliability cannot be ensured unless they are 100% tested and screened. Nothing to do with that. Okay? Who says that screening and testing it has to do with the reliability? Okay? I don't have time to emphasize this. Meeting absolute quantitative limit of reliability. They put a number in probably 0.99999, I don't know how, 4, 5, 6 nines, and you have to reach it. So everybody that knows how to manipulate the numbers will reach this, no problem. The real handbook 217 that was once the reliability prediction. What does it state? A reliability prediction should never be assumed to represent the expected field probability. He himself says this, not me. Okay, so this is already done. Plastic encapsulation parts cannot be used for space. So why? Because they are not hermetic. Who says that we are in a sport competition? Who is more hermetic? Nobody contests that the hermetic parts are better than the non-hermetic. But who says that the non-hermetic is not good enough? Okay, also, I don't have time. Quartz manufacturing is not controlled sufficiently. Who says so? Look in every website of those serious manufacturers, not all the manufacturers. You will see that it's controlled not by the government inspector that are cheated all the day. If you are looking at the guided alerts 20 years ago, or even more when there were even residential inspectors of the government, there were alerts that they found this cheated, this cheated. The serious manufacturers like National Semiconductor. Success in space missions can be achieved only by means of a conservative approach. So everybody knows that all the space projects are risky. Somebody that wants to avoid this, go to another business, I don't know. The redundancy is a magic. This one, it's true for also for the ceramic. I go forecast, we forget about it. Huh? It is. So remember that without electronics will be no spacecrafts. Unfortunately, now this is the Einstein understood it perfectly. He says we cannot solve our problems with the same thinking we used when we created them. And that is the summary of the presentation.
So good afternoon, everybody, and thank you very much, Mr. Dan Friedlander, for this very interesting talk. And you have a lot of experience, and it is very refreshing, actually, and challenging for us in doing new things. So the co-chairman is Mr. Frédéric Tillac from Hyrex.
Good afternoon, everybody.
And Frédéric will be introducing the first presentation.
So it's a pleasure to introduce Stephen de Cooper from Kinetic. Stephen is currently the head of the electronic and software department at Kinetic Space in Belgium. Before that, he acted as a project manager for the onboard computer product, the ADPMS, as used in the PROBA, the small satellites, and the intermediate experimental vehicle, the IXV. He will introduce you to the experience of using COTS on the ADPMS unit.
Thank you for the introduction. It will be difficult for me to present this topic after the presentation or the keynote speech of Dan, but nevertheless I will try. This presentation was actually built together by my colleague Johan de Hertog, which is the expert at Kinetic Space regarding components. This is the outline. I will skip this to speed up a little bit. Maybe some of you do not know Kinetic Space. While you're reading the slides, I can shortly introduce you by saying Kinetic Space is part of the Kinetic Group, Space and Defense. We are located in Belgium, Kinetic Space, and only focusing the space activities. For that, we had last month an inauguration of our new clean room, which is now 450 square meters and ready to be filled with many new interesting projects. Kinetic Space is active into, let's say, 4 business lines. We have started with the PROBA satellites. It's a project for onboard autonomy, and that's the first business line. The unit that I will be talking about, the ADPMS, is part of that PROBA satellites. Next to these satellites, we also make scientific payloads, which are to be launched and used within the International Space Station. That's a whole different story regarding commercial components than I will talk about today, which is part of our subsystems business, the onboard computer. Furthermore, we also have a second site in Belgium which is related to the downstream services. It's at Redu, and it's the ESA ground station that we are jointly with SES Astra operating. Okay, ADPMS. ADPMS stands for an Advanced Data and Power Management System into one enclosure. On the right hand side you can see a picture of that. It's a dual lane computer together with a power system, and it's built around a modular approach of the digital system. Important to note as well, it's intended as a platform computer, so high reliability, high quality then, and not really for a payload computer. It can also be used for payload computing purposes, but it's built out of very high reliable components. It's used as an onboard computer for the Proba satellites, for which the design already started almost 20 years ago, so it started around the year 2000, and it has in the meantime accumulated flight heritage on Proba 2, which last weekend we have the celebration of its 10th anniversary in space without any issues. But also gained flight heritage on Proba 3. In total, 16 years of combined heritage. At this moment, we are finishing off the 2 onboard computers which will be located into the 2 Proba 3 satellites. In between, we also made a spin-off of this ADPMS computer which flew at the IXV mission. The parts are generally class 3 level parts, but nevertheless we used around 20 different types of commercial components on a total of 300 different line items within this ADPMS unit. The design started in 2000, so which is way before ESA came up with the ECSS regarding the usage of commercial components. Why did we use these commercial components? It was basically because of functional reasons. No suitable flight equivalent components were available. However, we are 20 years later, market and availability has evolved, and now some of these components can be easily replaced or could be easily replaced by military or ECSS or IRL parts. However, as you know, if you are changing a design with heritage, you're losing your heritage, you might need to do a new qualification, and as you will see, we are having excellent performance of most codes used. The reason not to change it to COTS, it's definitely not because of a cost saving, because, of course, no doubt about it, the price per component is cheaper, but MAQ is higher, you need to do additional upscreening tests, you need to do radiation tests, you are subject to obsolescence and all kinds of issues. And it's also difficult to assess the total cost at the start of a project because of the various discussions to get COTS parts approved onto the units. So why then? Because of the design concept we used, I mentioned that we were using a modular approach. This modular approach was based on compact PCI components, connectors. We used multiple types to prevent inserting the digital boards into the backplane. Multiple types, we used 6 of them, type A, AB, B, and then the feed-through connectors. A second reason to use it was because of PCB space or area constraints. The decoupling of the CCGA and the MCGA devices, we had to use all 402 components, which at that moment in time were not available into the HRL series. But also, qualified parts are too large to accommodate. The dual Schottky diode, we use a plastic SOT23 package, which is currently not available into a commercial, into a HRL package. And finally, also some examples to be found in functionality and performance. Memories are a good example for that at that moment in time, and the low power analog housekeeping. So here you see some background about the compact PCI. So first we selected parts from Tyco with thin LED leads, which resulted in a press fit qualification campaign and extensive lot acceptance testing. Also a structural analysis was performed. We have faced some issues in the beginning with the hot oilery flow finish, which is not ideal for the press fitting, the mounting of it, due to tolerance restrictions, but also due to the ROHS directive. The manufacturers, Tyco in that particular case, removed the thin LED plating and went to a LED-free plating, which meant we had to change our compact PCI connector, and finally we selected the Harting ones. Again, a new press fit qualification and extensive lot testing was required. The current status is that, yes, there are compact PCI equivalent connectors for space available, but not really into these 6 different types. Another example was these 0402 ceramic capacitors, for which we used at that time KMET parts, which came with the traceability from an authorized distributor, manufacturer test level, which was specified. Thin LEDs, we did some additional solder qualification and some additional testing. But we encountered for that particular part some lifetime issues after some time. So we had procured in the beginning a big batch, enough for multiple ADPMS units, but in the end the solderability failed when doing tests for the latest satellite. So again, a new batch had to be procured, and the test campaign had to be repeated. And as mentioned, currently these 0402 size capacitors are now available. The next was the next reason was the PCB area constraints, for which I gave the example of the dual Schottky diode. We used the plastic package. If you have to replace it with HRL components, you need to have 2 diodes, which means more space, which at the time we did not have in our computer. In general, area is scarce anyhow. Here, additionally, we also had an issue with the obsolescence. So in the beginning, we selected a part from ON Semiconductors, which failed after the relifing after 7 years, so for the next satellite. And we had selected the component from a different manufacturer. But since it's a plastic component, we have to repeat the solder qualification, the testing, the complete test flow. So an unexpected cost and delay was introduced into the program. At this moment, there is still not such a solution available in HRL parts. Memories. I'm talking about the 2000 years when we started the design. So we are using commercial SRAM devices which are accompanied with our onboard computer. SRAM devices from Samsung and a NAND flash device from ST. In generally, the memory business in commercial off-the-shelf component is moving very fast. A decade ago, 1 megabyte was huge. Now you don't see it. It's gigabytes of into very small areas. So it evolves very, very fast that part of the commercial industry. So that's an issue. We overcome it with the fact that at the moment we procured already a large batch, which should ensure multiple usages into multiple satellites. Again, it's a plastic part, so again, solder qualification and radiation testing, which is very expensive on only very limited missions or projects. These very cheap commercial memories become in fact the most expensive parts used within our onboard computer. They are more expensive than the radiation hardened FPGA devices, which, as some of you know, are already very costly. But if you add up all the sums, all the money that we had to pay for these additional testing, the storage and so on, they are the most expensive parts. Obsolescence is always an issue, and you have to also be aware of variations in what they call a single lot COPS part. It was already mentioned this morning as well. So the current status is that we prefer external qualified devices, as for instance from 3D Plus. A last example was the analog front-end, which is built around to an RTX FPGA, radiation hardened. Also the power conditioning is radiation hardened, but the real analog front-end, consisting of a low power ADC, the op-amp instrumentation amplifier, were all commercial components. So again, with additional testing that was needed for this. But so far so good, meaning 10 years in space, low Earth orbit, no problems have been discovered, and still functioning fine. The conclusion, yes, no problem, COTS can be successfully used in space, but there are some risks of obsolescence. There are significant differences in batches and between manufacturers, and upstreaming costs per part are very high for small series. So if you take into account small series, COTS comes with a cost, and it's not the money saver for certain missions. Okay, that's it.
Thank you very much, Stephen, for your presentation. Very interesting. I think that we have time for one question, so feel free to ask. You should have a microphone. Do I have a microphone somewhere?
I will shout. On the ceramic capacitor, the issue that you found was related to the difficulty to stay within the specified profile of soldering of the manufacturer. Do you know that?
So the question was for the ceramic capacitor, if it was related to the mounting of the component.
The allowable let's say, profile that you...
The allowable temperature profile.
Because we know it is extremely strict for the commercial devices, far more strict than for space, because they have to be done with very, let's say, statistical numerous machines that are working on big numbers.
No, for the solder qualification, in the end, the assembly house managed to get it within the correct temperature profile, so no cracks have been observed. The main reason was that we used these commercial components was the PCB area for the 0402, I think at the end we had some issues of solderability, which was after the storage of 7 years.
How did you store them?
So the question was, how did we store these components? We did not store them within nitrogen at that moment in time. It was only in clean room conditions.
Okay, thank you very much. Thank you very much, Steven.
So then I would like to introduce our next speaker, Mr. Roberto Sibils, coming from INVAP. Roberto Manuel Sibils currently works at the Engineering and Production Division of INVAP, and he does research in aerospace and nuclear reactor system engineering, risk assessment of electronic systems for avionics and nuclear safety systems. His most recent project is the one that will be actually presented today about lifetime extension of electronic systems.
Thanks for your kindly introduction. Let me test this. Okay. I will introduce you some of the techniques that we are developing in BAP for extending the lifetime of codes that have to be used in space. You see, there is a new initiative, you know that it's a new initiative for new space, it's a movement, it's a philosophy, driving by new private companies and major traditional contractors of aerospace industry for access to space faster, cheaper and better by purely commercial reasons. It has new instruments, the small sats, constellations, lower production costs because they can apply large-scale production techniques and automation, lower launching costs per satellite because they use small sats, lower cost of components because they use COTS, but they have shorter satellite lifetime. There are several big players in this initiative, well known. Elon Musk, Red Weiler, Jeff Bezos. If most of them succeed, you will have soon 15,000 new satellites in LEO orbits in the next few years. So, we see here an explosive growing market. Assume $1 million per satellite of cost, including launching. That means $15 billion investment for the next years. What if we have the technology to extend the lifetime of these satellites? Assume 2 years lifetime per satellite. We will have to put in orbit 7,500 satellites to keep the services they provide per year. But if you extend just a little the lifetime, the number of satellites that you have to put in orbit decrease and the savings increase in the order of several $billion. So we have here an initiative that have an enabling technology that is the leading edge CMOS technology. But you cannot achieve space-qualified components using these technologies. So you have to use COTS. But COTS have lots of vulnerabilities these vulnerabilities trigger failure, early failures in the missions that are triggered by the environmental conditions: temperature, thermal cycles, radiation. But you can protect your devices from this environmental condition using low-cost techniques. Okay, this was the motivation. I will describe now some of the techniques of a toolbox that we are developing for protecting these devices in space. Temperature is an important environmental condition in space. You can have up to 50 degrees as ambient temperature inside the satellite. But your silicon have to suffer much higher because of operational conditions. Why? Because leading-edge technology has the highest power density in the history of electronics. That means a lot of heat in a very small volume. Plastic packages are not good for evacuating that heat. If you do not evacuate them, temperatures rises. So you cannot apply convection in space because you don't have atmosphere. And most of the components, the COTS, has the upper surface as one of good, is a good interface for evacuating heat, but it is seldom used in space. So, what is you have? A thermally conducting and electrical isolating paint, coating. You can paint your PCB, your populated PCB, and create a new path to evacuate the heat, reducing the hotspots, reducing the temperature in the silicon, and extending the lifetime. Another important environmental condition in space are the thermal cycles. You can have more than 8,000 thermal cycles per year in a LEO orbit. VGA plastic packages are one of the preferred packages for COTS. But VGA has extremely rigid solder joints. And the thermal expansion coefficient of plastics is very different to that of the PCB. So, thermal cycles becomes thermomechanical cycles, thermomechanical stress cycles that produce fatigue in the solder and its fracture. So what if you have a space-qualified anisotropic conducting film to join the PCB and the device, producing mechanical and electrical connections, releasing the mechanical tensions? You extend the lifetime of the electrical connection and of the system. Radiation is another important environmental condition in space. Somebody thinks that is the most important. It can produce single-event upsets and single-event functional interrupts, for example. But you can't mitigate them by using techniques like EDAC, lockstep, checkpointing, rollback. The problem is that it is not as effective as it would be to use these techniques with components that have not been designed for use there. So we are working in methodologies to make optimal their use with codes. Another effect of radiation is latch-up, is what is called latch-up. Latch-up destroys the chip. You can protect the chip using current techniques that shut down the power when latch-up produces. However, it is not too effective because latch-up is detected using a threshold that is far from the real power consumption of the chip. It is produced because the power consumption evolves along emission because of aging of the chip. So, what if you have a technique that uses an adaptive threshold very close to the real power consumption? You optimize the protection, you get optimal protection, and extend the lifetime of the chip. Radiation also produces what is called total ionizing dose. But you can reduce the effect of TID using spot shielding. Spot shielding is localized shielding. We are developing new structures and materials for optimal reducing of the effects of TID. Okay, we can see here a new initiative that demands extensive use of codes. But codes has lots of vulnerabilities. You can focus on looking for strong codes, stronger codes by upscreening, or you can focus in protecting them from the environmental conditions, taking into account the physical effects of the environmental conditions. Or you can apply both, making an optimal plan. If you do that, you achieve huge savings. Well, thanks for your attention.
Thank you for your presentation, and we have time for questions. I would have one concerning the adaptive latch-up protection. Can you explain us a little bit how it works?
Yeah, we have patented this very recently. The idea is to, in the orbit, you have regions of very high radiation and regions with very low radiation, 5 orders of magnitude of difference. So what if you have, you measure the proton flux and in the orbit and program the threshold when there is no risk of latch-up. And then, when you see that the radiation rises, then you apply the protection and do not program the threshold. This is the principle of the device that we are designing today. It's a chip, very small chip that you put in series with the each integrated circuit, having the information of the level of radiation from a central detector.
Thank you. I understand that by doing this, you decrease the probability of false triggering of the latch-up.
Yes, of course, because you have an algorithm that take into account the worst case and apply margin upper. So you don't have false triggering, and you protect from an optimal protection.
Thank you very much.
It's a great pleasure to introduce our new presenter, so Mr. Liu Hongmin from NSSC. Liu has been majored in physical electronics, and he joined the National Space Science Center, CAS, in 2003. Currently Director of the Quality and Reliability Assurance Laboratory. He's in charge of the parts quality assurance of Chinese space mission, but also the cooperation and the joint space mission between China and Europe. Thanks very much.
Thank you. Good afternoon. As this morning, my speaker mentioned that we have a lot of strategies to handle the costs, such as some standards, some ESA standard, NATA standard, or military standards. But in the practice, I think they cannot solve the whole problem. It tells us what to do, but do not tell us how to solve the problems in the quality assurance. So this maybe in some cases we may meet some actual problem and that did not mentioned in these standards. And this presentation will give an example to tell how we solve this problem. There's 4 topics: the advance and use of RD in space missions, and the quality examination of commercial IDs, and discussion on quality assurance that we meet some problem in the quality assurance, and some conclusions. The advantages of RDs is same as costs, especially it has high coherence, directional, and non-parental lights. This means it can do some sense experiment in space, and it's also in widely use in the high-speed network communication. This is some kind of Chinese missions use LEDs. The first one is quantum communication satellite, which launched in 2016, and we use same types of LEDs as used as the communication and use it generate entangled photos and do the quantum experiment. And the other one is Chang'e 4, which is landed on the moon in 1918, last year, and it used the laser to detect the distance between the lander and the surface of the moon. And also Chang'e 5 will launch next year, which means we will land on the moon and will return back from the moon to the Earth. And the next one is the Mars Explorer. It will be launched in 2020, and there are also several types of laser lasers used on it to detect distance, to detect the atmosphere of the Mars. And the other one is the gravitation wave detector, which launched August this year. It uses the laser coherence to detect tiny distance caused by gravitational wave. So this sample means if we handle the costs values carefully, it means it can work properly for a very long time. But all the lasers now is costs. There is no military or special level for it. So it means there's no consideration of commercial vibration in launch stage and also in the landing stage, and then also vacuum radiation environment in space. And there's no reliability test and assess of lifetime. So now information about design, changing and manufacturing process, delivery and storage for end user. For yes, that means this is the disadvantage of the commercial lights for our end users. So this is our quality assurance flow. It's used in the LED quality assurance. We add a evaluation test in this quality assurance flow. And we do not use the qualified stage. We just use lifetime and DPA to replace the qualified stage because we think it is reasonable for the LD use for our mission. For construction analysis, we will confirming the construction material technology and the component analysis to determine the items that we use in the actual test or evaluation test. This decide what we will do in the quality assurance. For the evaluation test, we will to estimate the ability of working normally in the space. For example, for the constant acceleration, in standard we use 5G or 1000G. But for this part, it is correct for it. So we must evaluate. So we'll select reasonable constant acceleration to do the test. So the final one is the normal screening lifetime MDPA. Take here example for DBF butterfly package LD. So we know the circuit and the construction and the physical LD is here. So from this we know it's a sealed butterfly package, and it has package material, soldering material, and metal casing and fiber material, all this material. And the technologies, soldering technologies, bonding technology, welding technology, and the sealing technologies. And parts have resistors, and LD chip and photo chips. So from construction analysis, we found the weakness of the commercial LDs, such as its solder material is QT. So it is will subject to the risk of twin whisker, and this all the weakness of the commercial LDs. And also we do the analysis for the LD chips, and for some kind of LDs we found some defects in the LD chips, such as the picture, the photos tell us there are some strips or cracks near the active area. It means if we use large current or use large power, it will lead it will let the strip or crack grow quickly to the active area, so it will lead to the failure of the LDs. So this is the elevator test and the action we will take. For example, for the solder material is QT. We have two measures. We use PB37 and SN63 instead, or we do the evaluation test to see how long the tin whisker will grow. And this is the action we'll take. And also for the evaluation test, and more than 10 types LD, we do the evaluation test, and we cooperate with author, do this some results published in this article. So before I introduce some confidence flaw, but here I will show some problem we meet in the quality assurance. The first one is the output power changes. For LD with the fiber, the output power changes after the 10 temperature cycles. The reason because the fiber is mounted in the metal case, and the metal case is used laser widening connected to the case. So when we do the time cycle, the mechanical stress will release, so lead to the change the direction or position of the metal casing. This leads to the power drop. So the position and the direction change of the metal casing can be repaired, but cannot be recovered. So the repair was exactly after 10 cycles of 10 cycles. The one which cannot fix it less than 10% will reject, but not count into the PDA. But if it count into the PDA, the whole batch will be rejected. So this will lead to no LDs can be used. The other one is the burning conditions and lifetime test. For construction lines, we know there are defects in the LED chips. This will expand under the influence of current and temperature. We have to do some tests for 1,000 hour and 2,000 hour lifetime test, and we meet some failures. That's because the defects expand to the active area. So, for end user, the detailed information of our LED chip is unknown. So the condition of burning and the lifetime test, such as the value of power out, IF, VLD, and the temperature of TC, are reasonable considered according to the working conditions and the orbit. This meet the keynote speech in this afternoon. So we must consider the test conditions reasonably, not just according to some standards or some standard or some document. And another one is a discussion on the assessment of the quality of LED. Usually, in this standards and this document, all the quality assessment is based on the parts parameter. For example, for LED, we use power out, ITH, IF, and the curve of PI. So usually, the temperature are tested and to assess the quality of LEDs in really standard. For commercial LED, there is higher discretion of this parameter in batch. This is what we need. So it's hard to select good one to be assembled in system. For example, 2 LED with the different power out, but with the same power changes. After burning test, it is hard to tell which one is better in quality. So we have some discussion of the assessment of quality of LED. As this is this action we take is the assessment based on the PN junction parameters. It has been researched that using PN junction parameters derived from LED parameters to evaluate the quality, the PN junction parameters are M, H, B, and P. For example, for laser level, M represents the material quality and the technology level. If M is small, it accounts for that defects. Isolation and the internal stress damage in the expansive layer are relatively small. So we use these parameters. We can solve the problem I mentioned above. So this is the article and published in IEEE. So now we can come to the conclusions. One is some commercials have been used in space very well and will be used in space further application. The other one is there are some defects. This will go under the influence of current temperature. So the test conditions of screening and qualification must be considered reasonably according to type, working environment, and conditions. For example, if for the Earth orbit, for the Moon orbit, for the Mars orbit, the conditions are quite different. And for 1 year mission, for 2 years, and for 3 missions, the condition is also quite different. So we must consider the quality assurance test condition carefully. And for commercial LEDs, their parameter PN junctions are useful to describe the quality and the reliability of the LED. So this the photo on the top is a scene of a mission that China cooperation with European with ESA. So we have a lot of cooperation with European agencies and other companies. So in here, I also welcome the company and the agencies have cooperated with China. Thank you.
Thank you very much, Liu. We have time for one question. I have one. Just focus on the LD, the laser diode plus the fiber, okay, which is at least a complete module, I would say, because you got the resistor, you got the TEC, you got the laser diode and the fiber. what will be your approach? Do you perform the qualification at the system level, I would say, or do you want to perform the qualification or the characterization at each component individually?
At each component individually, not at the same.
Okay. Any other question? So, thank you, Liu.
So let's switch to the next talk. Actually, it is my pleasure to welcome here Sophia Ruiz-Martin from the company Sener. Sophia holds a Master of Engineering in Electronics Engineering and a Master of Science in Motorsport Engineering from Oxford Brookes University. So she joined Sener Aerospatiale in 2018 after working for 5 years, actually, in the British automotive industry. And in her current role as electronic system engineer, she's involved in the assessment and the selection of COTS components for defense and space applications.
Thank you, Philip.
You're welcome.
As Philip has kindly introduced, my name is Sophia Ruiz, and I will be presenting today the use of COTS in space missions at Sener Aerospatiale. The presentation is structured in 5 blocks. First, we will see a brief overview of Sener Aerospatiale. We will then move on to discuss a little bit our heritage with regards to using COTS for defense applications, which will lead us to discuss the use of COTS in space applications in terms of our motivation, where we are right now, and the main challenges that we are facing in the process. Then we will discuss the future opportunities that we see for COTS in space, and finally we will wrap up the presentation with the main outcome. So, Sener is a private engineering and technology group which was founded in 1956. Only 10 years later, it started its aerospace activities, and it was the first private Spanish company to do business with ESA, which was one of the predecessors of ESA as well. As of 2019, Sener Aerospatiale, or Sener Aerospatiale, is an independent company within the group, encompassing the defense and the space business units. And it now also includes the companies formerly known as Trio and Rimsa. And just a very, very quick remark is that, as you can see Sener Aerospatiale within the Sener group, you can see several divisions: Flight Systems and Avionics, Electromechanical Division, but you will not see a separation between defense and space, and that's because each division works for both businesses. So, COTS in space is a fairly new topic. It's gaining a lot of traction. It definitely draws a lot of attention, but this is something that we saw happening before in the defense industry. The defense industry is a high reliability market, and it has a service life for electronics of 25 years. And for the last 15 years at Sener Aerospatiale, we have been using a combination of MIL-qualified and COTS components. The manufacturing process for COTS components is controlled by PCNs, by part change notices, and we have implemented obsolescence systems, which has been mentioned before in other presentations, is key when dealing with COTS. We have also developed a design methodology for achieving high reliability using COTS components, and we have taken into account elements like derating and incorporating considerably higher design margins when you incorporate COTS. And finally, we have acquired experience using plastic packaging and high-density packages like BGAs and leadless, and achieving high reliability soldering assemblies. So right now, Sener is in the process of transferring our heritage in production electronics for defense into the space market, especially in the applications concerning processor and driving electronics and control. And one of the things that we really want to get across from what we've learned in defense to space is the fact that reliability does not only depend on the component, on the package itself. Yes, sure, that's key. But you also need to make sure that your assembly is reliable, that your system is reliable. And one of the things that I've mentioned before is that the know-how and personnel is shared across defense and space, so that is definitely something good for us when we want to get across that information and that experience. So at Sener Aerospatiale, we see COTS in space as an emerging market driven mainly by 4 factors. One of them is state-of-the-art devices, which has also been mentioned before. I mean, COTS offer a better performance, and usually a better size, weight, power consumption, and they're also readily available, and the lead times are considerably shorter. Also, development kits are readily available. You can order them, have them in a couple of days usually, and you can get samples as well very quickly. There is also a lower upfront purchase cost associated to COTS, and that for non-large-scale integrators like ourselves is key, especially in the current competitive space market where we are being asked to offer our products at lower prices, and we need to be able to compete with larger organizations in the new space scenario. There is also the appearance of disruptive new customers who have arrived to the space market, challenging the way we do things and with profit in mind, and trying to bring down the costs for satellites and launch vehicles. And finally, the fourth element that is motivating the introduction of COTS in space missions is the evolution in control of the manufacturing methods used for commercial components, which is resulting in COTS with higher reliability figures. So traditionally, we see that the high reliability designs in the space industry were based or were sustained by 4 pillars: strict control of the raw material, a well-controlled manufacturing process, extensive screenings, extensive testing in the qualification process, and finally, extensive screening at component level. The issue is that the way to sustain these 4 pillars has been basically it's been sustained with standards that were initially developed in the 1990s. For instance, MIL 217F, which is the primary source for reliability predictions at component level, was thus updated in 1995. So the technology and manufacturing processes have improved considerably through the years, but those improvements have not been taken into account by the standards. And we can also see that right now there are other markets which are successfully evolving their manufacturing processes, like automotive, like defense. They're achieving high reliability figures, and that leads us to the necessity to develop new ways to calculate reliability. But one thing that we really want to make sure that everyone gets is that we believe these pillars are still valid. We want to incorporate COTS in space missions, but our reliability figures still need to be good. However, it is true that the extensive testing in the qualification process and the extensive screening do drive up the cost considerably. We put here a couple of examples, so a diode and a quad comparator. We have the military grade and the equivalent space grade, and even if it's the same component, the same die, the same factory, the same manufacturing process, just the extra testing and the extra screening can impact the cost considerably. So incorporating COTS in defense and then incorporating COTS in space led us to develop a methodology that is basically as follows. We believe that a deep understanding of pillars 1 to 3, which is raw material, manufacturing process, and qualification testing, will lead to reliable components. Robust component selection and design practices will lead to reliable designs. Appropriate assembly and good inspection techniques will lead to reliable assemblies. And finally, obsolescence monitoring will lead to design maintainability and reuse, which is key. In terms of our current space missions, we have a few where we're incorporating COTS. I've picked one, which is Naviga. We're currently working with Avio to develop the new navigation system for the new Vega C launcher. And one of the challenges in this project is to bring down the procurement cost. So in this case, we're trying to use COTS to meet the targets that we have in terms of procurement cost. However, the project requirements make it really hard to introduce COTS or even space COTS. For instance, most space COTS have different TID characteristics, but most that we found, they say they can withstand 20 kilowatts for TID, and they can withstand 43 for cell. Well, that's what they say is needed to survive for 5 years in LEO. However, the project requirement for this launcher says that every device that goes on board has to be characterized up to 60 mega electron volts. So we find that there is a gap between what space COTS manufacturers are offering and what we need to be able to ensure. And the only way to cover those gaps is through testing. This is just for radiation, but there's also other issues that you might consider. And one of the things that we are finding is that there is a lack of cooperation from manufacturers when it comes to doing extra tests and extra screening. So I've already got ahead of myself talking about the challenges, but we've outlined some of the ones we are facing in our ongoing projects. The first one is that there is a wide range of COTS. So we have military, space COTS, automotive, we have industrial, and out of those, space COTS are usually preferred. But the range is very limited. Not a lot of people are launching products in this range. They're usually rad-tolerant devices, though the prices are more expensive than the automotive qualified components, like 50 times more is what we find. And there is no unified standard. So each manufacturer will say that something is a space COTS, and then you'll find that the other one says something completely different in terms of data. So there's a mismatch, and there's no unified standard. Automotive COTS, well, there is a lack of radiation and reliability data for them. And even just lack of, it's hard to access the qualification data if you're not an automotive OEM. So access to the PPAP data qualification is not readily available for everyone. And they're usually ROHS compliant, which means that the terminations tend to be pure tin, and that leads to the whisper concerns that we've discussed in previous presentations. And also we find that companies that are testing with COTS are not sharing the information, that are testing for radiation, so there's no availability of reports, there's no cooperation, because it gives them a competitive advantage. And we also see that there's like a high non-recurring costs associated to COTS in terms of MOQs, staff screening, which can burden smaller companies. And there's also the issue with obsolescence that we have discussed earlier. And also the fact that it's hard to get AAA parts manufacturers to cooperate when you need to do the extra screening, as we're seeing in Naviga. And also the fact that if they do have a Class 1 equivalent, they're not going to be very keen for you to use a COTS or a space COTS. So it's kind of hard. And some of the lessons that we're trying to move from our defense experience with COTS to our space business is first of all that we can find some of the issues that we've been finding in defense. There's a way to mitigate them, like pure tin. So using pure tin and the whisper concern has been addressed before in some military standards that are available to use, and they can lead the way. Also, using new methods for reliability prediction, like it was mentioned earlier, like FIDES or other customizations that you can use to get actually figures that are closer to what we're seeing in field return. So in defense, using COTS and using the military standard, MIL 217F, you get sometimes very pessimistic figures. And then we see the field return is actually way better. We have developed an experience using enhanced plastic packages, and that we're trying to move across to our space expertise, especially enhanced plastic packages which were developed for harsh environments and that are now being launched for space applications. And finally, the implementation of obsolescence management systems. Someone mentioned earlier that if you test cost for radiation or whatever costs, then that information becomes obsolete the moment you get a PCN. So that's no longer valid. So you need to really keep an eye on every change the manufacturer makes to the process, to the wafer. Everything has to be controlled. In terms of future opportunities for COTS in space, we see first of all the possibility to offer competitive recurrent prices, fundamentally in two areas: for low orbit, short duration missions, and also in missions where there is a high degree of recurrence. We see the possibility to access new markets like constellations and approaches, new space. And also the ability to use state-of-the-art designs, modern components, and replicating what other markets are doing with more advanced architectures. And in our case, it gives us the opportunity to transpose already proven designs that we have developed for defense, and vice versa. So actually have a cooperation between what we do in defense and what we do in space, knowing that the architectures are functional. In terms of conclusions, the first one would be that COTS are mission enablers in terms of performance, cost, and availability. They allow for a greater degree of collaboration across different markets. But new methods for reliability prediction are needed. Also new standards for space COTS in order to know what we are actually purchasing. And finally, that obsolescence management is key. Thank you very much. Muchas gracias.
Thank you. We can take 1-2 questions. I have, I have one question, Sophia. Actually, having access to, you allude to the fact that having access to data is one problem, one difficulty in using COTS components. What would be the steps to put in place in order to improve actually accessibility of data?
Well, I think sharing information is key in this case. But I think that similarly as we form consortiums in order to develop satellites to engineer systems that we put in orbit, we should be forming consortiums probably to share that information and to actually collaborate in terms of that kind of data. Also, our companies don't have enough volume in order to go to automotive manufacturers, for instance, and asking for qualification data for automotive component manufacturers. But as a whole, as a collection of entities, we probably can. So I mean, it's the usual we're better together, but I think it's a matter of cooperation. I mean, component level engineering is just one bit, but system level engineering is what actually sets us apart from each other. So that's what the competitive advantage is. I hope that answers questions.
So together we will be stronger. And this is what we try to do today.
Thank you so much for today. Thank you.
So it's my pleasure to introduce our next speaker, Ferdinando Tonicello from ESA. So Ferdinando, after working in the space industry for 9 years, joined ESA in 1997. He has been working in power management and distribution domain for various ESA programs as a technical officer in a number of ESA R&D activities. In 2015, he was appointed power management and distribution lead engineer in the electrical department, the TEC-E. His COTS experience comes from some pioneering work on comparative development of power conversion stages based on IRL versus commercial components. Thank you, Ferdinand.
Thank you very much for the introduction. We'll report you about the work that we did in ESA that was previously, mentioned by my colleague Mikko Nikolainen, and refers to the work that we did in a big group of persons about trying to derive some guidelines for the space, for the use of COTS in space for institutional reasons. So basically, what we are addressing is not, guidelines for generic use of COTS, but trying to get guidelines for COTS for institutional missions. That is very different than having something to do with big constellations or other commercial purposes. Okay. First of all, I don't think we have to dwell too much on these reasons because they've been over and over and over again. Cost advantage, maybe alleged cost advantage, we should say. If you have the large volumes, where are the large volumes, by the way? Performance advantage, for sure. It is really where we can make a difference because, in fact, it's already happening in ESA a lot. COTS are used a lot in ESA. Maybe it's not known, but even major flagship missions use the key, COTS devices and even boards, because there was no other option. Lack of IRL components performing function, also very common. Availability of production capability, supply chain of terrestrial use, but we've seen that sometimes this is counteracted because it's not said that you might have access to all COTS devices that you want to access, especially for automotive. And maybe shorter lead times. Okay, what we did in ESA is this thing. It's just a replica of what Mikko showed this morning, a little bit more in detail maybe. I don't think we have to go too much in detail here. Basically, it's an activity that is going on since 2018, February, and hopefully will end up before mid-2020. All, directorate in ESA has been involved into this. Not only components engineers, because of course, as we have understood before, it's a matter of, how would I say, concurrent engineering. It's not a matter anymore of isolated component guy deciding if the quality is good or not against the standard, but it's a matter of understanding from application perspective and so on. What we need to produce by the end of the period
is a set of recommendations for the use of COTS in future agencies programs. You see no space covered here, and roadmaps and required next steps to achieve them. This is the extended version of what has been shown before, that show a little bit the thing that I said. We have a steering committee headed by Britta, and then 2 working groups. Now I will explain what we have been doing there on each one of them. I'm the convener for the group 2-3, because originally there were group 2 and 3, and then at the end it was too much splitted, and we decided to put them together. But as you see, the type of expertise that has been covered, it goes far beyond just the component engineer, because we understand that, in fact, you have to make a compromise, and the compromise comes out from a lot of voices together. The 2 groups had the following tasks to cover. So basically, working group 1, the definition of COTS-EEE components, perimeter for space, understanding the landscape, where do we stand today, and how would we use COTS today, and current best practices and lessons learned. ACID is one of them, maybe the top of this exercise. Working group 2-3, it was to perform a classification of COTS in components categories according to criticality categories. Let's see what we're talking about. Identify procurement, screening, and application, and test methods for COTS components for these application criticality categories. Identify a roadmap or the activities that are needed to have a final approach. What we came to is a document, is a set of guidelines, is this document, Working Group 2-3 Work Synthesis. And it is a set of guidelines, they're not requirements, so because we have understood that we cannot throw requirements on this, really, especially at the beginning. We tried to get a kind of balanced approach between reliability and radiation performances according to progressive scheme of higher to less risk-taking. It addresses the big problem of small procurement lots and lot homogeneity issues. We have understood that this is a parameter of very much importance to do it right. And maybe the most important thing is that this one, that the goal was the following, and we understood that maybe the application of COTS parts in modules, equipment of such system or different criticality is needed. So basically, it's a little bit different than the approach that we used before, because before we would say, look, this mission is class 1 components, full stop, we cannot discuss it. Now, the idea is different, is that equipment in that mission is that criticality, because maybe it depends on the essentiality of such a function inside the spacecraft, and it could be that you can accept, even for a flagship mission, you could accept the COTS, for example. It depends on what you use it for. Do I want to take big pictures? I use a camera from a commercial manufacturer, I do the minimum test needed, and have fantastic, let's say, deployment vision of the satellite, let's say, being deploying the solar array and so on. If it doesn't work, tough luck. I will not say to the public that I have the camera. But if I get it done, maybe you will save a lot of money and you do it right. So this one is maybe the method that the group concluded at the end. On a given mission, different criticality categories can appear depending on the nature of the considered module, equipment, or subsystem. Basically, the reasoning is the following. And here is a kind of a summarizing table of the note. So basically, we said, look, we divide the world in 2 parts, a green part and a yellow part. On the green part, we have where we expect trace code homogeneity, to speak very simple, just not to speak it. Because of course, for radiation aspects, you have to go down deeper. You have to go down to diffusion mask, to wafer fab, and so on. But we said, there we expect to have homogeneity, and therefore I do a test here on ground, and I know I have a good reason to think that what I will fly will be the same quality. What I do there is a kind of a normative area, because if this happens, you can apply testing and you can apply requirements. So, and the approach is, okay, let's use the standard that we have already. Of course, it has to be updated because it has to cover also passive components that at the moment it does not. And already there we have 3 classes of components that will be decided case by case or how to apply. On the yellow area, we open up to something different, that is, we are not sure of the trace code homogeneity. And if you are not sure, does it make sense that I spend so much time to do test here on ground and then I fly something different? No, it doesn't make so much of a test, of a sense. So what here is proposed is to have a set of guidelines agreed with experts and hopefully extending this note to you, because that's what can be done, and we'll come back later to this. And here we identify the 2 classes of components, not components, of subsystem equipment module criticality. One that is the wildest one, Q2, and an intermediate one that is Q1, where you do additional tests. Let's see something more in detail. The color scheme is the same as before, so we have a normative area. I will call it IRL certified mission, because what we pay sometimes in space is a lot for the certificate of conformity, more than for the quality behind, because the quality behind we don't know too much what it is. So basically there you use the Q6013 or the Q60, that's it for IRL. On the other one, basically what we identified is the limitation, but it's just a limitation of, let's say, convenience, and it can be discussed. Of the first class is adapted for something that is low-cost experimental, that is limited in time to 1 year to reduce the probability of single event effects, that is limited to 5 kilorad, such that you, even with the normal components, you have a chance to get it through, to have success, even though you're not testing a lot, or you're not testing at all. While, of course, in the intermediate case, in the class Q1, we will identify basically something that is in between the 2 worlds, and where you need to do some testing. You need to have a little bit more, I wouldn't say certainty, but you need to be relatively sure that you made all what is possible to be sure that what you fly is exactly what you tested on ground. Okay. So we covered for each one of these criticality categories the perimeter of application, as we have seen before in the previous chart. But of course, we call the RAMs, material and processes, the generic issues around the Tripoli components, which requirements or which recommendation, not requirements, recommendation you want to give for radiation, for total dose, ionizing, non-ionizing, single event effects. To understand something around the economy of scale, supply chain, because it's very important. Well, basically, where are you procuring your component from? Are you procuring them from distributors or from the manufacturer? Do you have a special contract? Or is it just you go to a distributor, I want to have a bag? How do you know that the bag contains similar devices? You don't know. So you have to understand these things, basically. And finally, application. We're seeing how application is important in this concurrent engineering aspect, because there, basically, we need to have an approach for the datasheet review. You know, datasheets, if you read any commercial datasheet, it will tell you something very interesting. It is said, look, I reserve the right to change this information, the product, and not even to tell you. So you have, if you want to be sure to have a certain performance out of the device, you have to check yourself. It's not that somebody will do. It will cost money, so it's against the cost saving. So it's a little bit of an issue. And then extensively we went through electrical analysis needs, the mitigation techniques that are needed per class of components at component level, at board level, and system level, reference application circuits and modules. At the end, we gave a number of 7 recommendations to be, let's say, hopefully subscribed and paid for, because the recommendation means, in fact, you are asking for man hours, if not money, to do things. And this is what we came through. So, first, it is a factor. I think we will not have a problem with the update of the standard, the Q6013. We want to identify safe operating factors for criticality categories Q2 and Q1. What does it mean? Imagine for Q2, we are limiting it at 5 kilorad. And we say, look, if I take a class of components, and I'm talking of class components of a simple type, like transistors or MOSFETs or maybe comparators, not too complex circuits, it might be that you're able to identify what is the range of variability of the critical parameters of these components, put them into a database, and say, look, this information is available. If you have this information, maybe you can design in Q2 up to 5 kilorad without doing tests. You take a certain risk, maybe you have to do something, but still you have something to do. Then, COTS component and modules, information gathering. We are all here, we understood that this is fundamental to do. We need to have more information and more shared. We have seen many opportunities here to do it. And then, reference application circuits, because there we have understood that special radiation performance comes with a circuit defined in a certain way around the component. You cannot really separate the component from the way it is used. You have to bias it exactly in the form that you want it to do, to be sure that it has the same performance that you verified by test. And then, new test methods for modules and boards, even though the black box approach is not really supported, because we are not sure what is inside. You might have seen the presentation by Sam this morning. Finally, lead-free recommendations and good practices for radiation from our, let's say, environmental group. Okay? Basically, this is it. What I wanted to tell you is that the note, after internal discussion, can be made available to anybody of you on request if you commit to give comments to it. Okay? So here is my address and number in case you want to come to me for this reason. Thank you very much.
Thank you very much, Ferdinando. We managed well. We have two minutes left before the break. So if there is any question, feel free to ask. Yeah. Is the microphone somewhere?
My question is about the slide, your slide number 8, slide 8.
Can we go back to slide 8, please?
Could you say where you can place the CubeSat mission?
I would say CubeSat for LEO that are lasting not more than 1 year were put in Q2, because you don't have more than 5 kilorad, and maybe you don't need to do more than that. The issue is also if you are having let's say the need to do a lot or not. If you don't need to do more, why do you do more? And of course, it's not a matter of let's say prescriptions, because here the note will only contain, let's say, recommendations. Then if you don't do it, it's your business. But it will be, of course, it is the best compromise that we found among a lot of different experts, both at system and component level, material and processes, radiation and so on. So maybe it's worth looking and try to adhere to it, even though they're just a recommendation, because they are, let's say, the best we could came with. And hopefully, if other people will give inputs, it will be great, because we can improve it further for the benefit of the community.
Second question here.
Nice. Thank you. Nice presentation. Hello. I guess I have to yell. Nice presentation. And that makes a lot of sense to group your standards in lifetime radiation environment, etc. But it becomes very difficult for others to adopt your standards if they're qualitative, as you have made them in many instances. So the cost and life, cost in particular, is a very relative qualification. Have you specified that a little bit more?
In the note, if you might want to have the note, you will see that it's structured in a way. It is structured like an ECSS document, where all sentences are written in terms of should. If you want to have a, let's say, a full, let's say, requirement set, change them in shall. It's as simple as that. So, meaning, we are not ready yet to give prescriptions, because the reality that we see is that we have to be adapted each time to something different, and it's not so obvious to have a single solution.
Perhaps we can take that offline. I meant to make a different point. Cost and reliability, you classified as low to medium or high, and that is an extremely relative term, depending on where you come from. And so I wondered if in your document you have been able to make that more specific.
We can make it, maybe is already your comment to the document. We can make a boundary that is more specific. Of course we can do it. And it is relative to, let's say, the ESA world, because it has been developed for ESA use. It's not a document for, let's say, for external, let's say, we are not intending to say how one web has to do. No, this is not the case.
Thank you. I would like that we thank you all the speakers for their presentation once again. So let's have a break, and let's be at 5 p.m. sharp here to continue. Thank you.
C'est aussi simple que ça. Il n'y a rien de plus.